In this presentation, we're going to look at the structure of atoms and how that affects their reactivity. In this class, we're going to limit ourselves to considering the simplest model of the atom, the Bohr model. In this model, the atom is modeled as a nucleus with protons and neutrons surrounded by a cloud of electrons. The nucleus is positively charged because of the presence of the protons, and the positive charge attracts the negatively charged electrons as they orbit the nucleus. So let's start with the simplest atom, hydrogen. In this case, the atom has one proton surrounded by one electron. The atom as a whole has no charge because the negative charge of the electron offsets the positive charge of the proton in the nucleus. Notice that in this model of the atom, the electron has a fixed distance from the nucleus. If we look at the next most complex atom, we find helium, which has two protons and two electrons, and actually two neutrons. Again, the electrons occupy the same region of space called an electron shell. This electron shell is the closest to the nucleus, and we call it the first electron shell. Notice on the periodic table above that both of these atoms occupy the first row, or the first period, in the table. This signifies that they both have electrons in only the first electron shell. If we move from the left to the right in the periodic table, we get to the end of the row with helium. This shows us that the first electron shell is full when it has two electrons, as we can't go further to the right in the table. Before we continue, I should state that elements are different primarily because of the number of protons they contain in the nucleus. If an atom has one proton in the nucleus, it is hydrogen. If it has two protons, it's helium. The number of protons in the nucleus is known as the atomic number, and the periodic table is primarily arranged according to atomic number. If you add up the number of protons and neutrons, you get the atomic mass. In the case of helium, it's 2 plus 2 is 4 daltons. You may notice that the atomic mass for helium is given as 4.003. You may also know that protons and neutrons have exactly the same mass of 1 dalton each. Therefore, how does helium have a mass of 4.003? Where does that extra 3/1000ths of a dalton come from? Now, you may also know that protons and neutrons have exactly the same mass of 1 dalton each. The mass of electrons is negligible. The answer to this is that some naturally occurring atoms have 2 neutrons to give a mass of 4, but some rare helium atoms have an extra neutron, giving them a mass of 5. If you average out all of the helium atoms that occur naturally, the average atomic mass would be 4.003. Now, let's get back to adding protons and electrons and move down one row or period in the table and look at lithium. Lithium has 3 protons and 3 electrons. Notice that the third electron can't fit into the same electron shell that the first two are in. It needs to go into a larger electron shell. Notice also that since this element is in the same group or column as hydrogen, it also has 1 electron in its outermost electron shell. We call this outermost electron shell its valence shell. When two atoms come in close contact with each other, they may react. Whether they react depends on whether they're more stable apart or together. In the case of hydrogen, two atoms each have a single valence electron. Individually, they're unstable because of that single valence electron. It exists in a valence shell that isn't full. A reaction between the two atoms allows them to share electrons, and this sharing means that they both have a full valence electron shell and are therefore much more stable than they are alone. This kind of bond is called a covalent bond. In covalent bonds, electrons are fully shared between the two atoms. Notice that even though we draw bonds like this, with two electrons directly between the two nuclei, in reality, the electrons are spinning all through that electron shell. Let's look next at methane, which has a single carbon atom surrounded by 4 hydrogen atoms. The carbon atom has 4 valence electrons, and each of the hydrogens has a single valence electron. In the formation of methane, 1 electron is shared from the carbon with each of those hydrogen atoms. Notice that in the final structure, the carbon has 8 valence electrons and therefore has a full valence shell. Similarly, the hydrogen atoms each have a full valence shell of 2. A covalent bond is the sharing of 1 pair of electrons. In some compounds, more than 1 pair of electrons can be shared. In ethene, the carbon atoms share 2 pairs of electrons each. One of them contributes 2 single electrons, so collectively they share 2 pairs. This is called a double bond. Triple bonds with 6 shared electrons, or 3 pairs of electrons, are also possible. It's often useful to show how the electrons are distributed in the electron distribution diagram. However, it's often more convenient to show a structural formula where we represent a pair of shared electrons as a single line. Double bonds are shown with 2 lines between the atoms. In covalent bonds like these, the atoms are held together by the shared electrons. If the atoms were to split apart, they would become less stable than they are when they share electrons. Unlike in covalent bonds, which are characterized by shared electrons, ionic bonding involves the complete transfer of 1 or more electrons from one atom to another. In sodium chloride or table salt, the sodium atom has a single valence electron in its third shell. The chlorine atom has 7 valence electrons in its third shell. Both atoms individually are unstable because they have an incomplete valence shell. By transferring a single electron from the sodium atom to the chlorine atom, the sodium atom has a full valence shell, and the chlorine atom also has a full valence shell. They're therefore much more stable with their full shells. The atoms are now known as ions because they have more or fewer electrons than they do protons, and they therefore carry a positive charge if they have fewer electrons and a negative charge if they have more electrons. In this case, the positively charged sodium ion is attracted to the negatively charged chlorine ion because of the difference in that electrostatic charge. So, why do some reactions form covalent compounds, whereas others form ionic compounds? To answer this question, we need to look at the electronegativity of the reacting atoms. Now, electronegativity is a measure of how strongly the nucleus pulls at the electrons. Small atoms have valence electrons very close to the nucleus, and therefore the nucleus pulls very strongly at those electrons. Larger atoms have valence electrons much further away from the nucleus, and the nucleus exerts a much weaker pull on the atoms. You can see this trend if you look at a vertical group in the periodic table. At the top of each group, the atoms are smaller and have electrons closer to the nucleus. Further down the group, the atoms are larger and the valence electrons are further from the nucleus. Similarly, as you go from left to right across the periodic table, you get atoms that have more protons in the nucleus. As the number of protons in the nucleus increases, the force exerted on the valence electrons also increases. Therefore, the electronegativity of the atoms at the top right of the periodic table, excluding the noble gases, are the most electronegative. Now, let's get back to why some atoms form covalent bonds and others form ionic bonds. The difference lies in how big of a difference in electronegativity there is between the two atoms. Take, for example, 2 chlorine atoms. They have the same electronegativity and therefore pull at the electrons equally. This results in sharing the electrons or a covalent bond. On the other hand, sodium and chlorine in salt have very different electronegativities. As a result, the chlorine pulls the electrons much more strongly towards its nucleus than the sodium atom. In fact, it pulls the electrons so hard that the sodium pulls so weakly that the chlorine completely strips the electron from the sodium, resulting in an ionic bond. Now, you'll notice in this diagram that there's also an intermediate case. If the difference in electronegativity is moderate, then the sharing of electrons is unequal, but a covalent bond still forms. We call the unequal sharing of electrons a polar covalent bond because it results in a polarity of the bond, with the more electronegative atom having a negative or partial negative charge, and the less electronegative atom having a partial positive charge. For biologists, the most important example of polar covalent bonds comes from the water molecule. In water, the oxygen atom is much more electronegative than hydrogen atoms, but the difference isn't so great that the oxygen atom completely strips the electrons from the hydrogens. Therefore, the resulting bond is a polar covalent bond. In this case, the oxygen pulls more strongly, and the electrons end up closer to the oxygen nucleus than they are to the hydrogen nucleus. As a result, the oxygen has a partial negative charge due to these extra close electrons, and the hydrogen has a partial positive charge due to their lack of electrons. Until now, we've been talking about intermolecular bonding, that is, bonding within a molecule. However, molecules also are attracted to one another under certain circumstances. The strongest of these intermolecular forces is called hydrogen bonding, and it's a result of the attraction between a partial negative charge and a partial positive charge. Let's see how that works in the case of water. Every single water molecule has both positively charged and negatively charged regions. The positively charged regions around the hydrogen atoms are attracted to the negatively charged regions of separate water molecules. This attraction holds the molecules together, but only briefly, as it isn't strong enough to fix them in place unless the temperature is really very cold. We'll learn about that more in a later lesson. Another very weak intermolecular force is known as the van der Waals force. These forces are as a result of the uneven distribution of electrons at any instant. If electrons are unevenly distributed in one molecule, just by the chance of where they are at a given moment around the nucleus, there will necessarily be a region of the atom that is just momentarily partially positively charged, another region that's partially negatively charged. These small differences in charge can cause an attraction for other molecules. In order for van der Waals forces to exist, the molecules must be very close to each other. Van der Waals forces are individually very weak. However, when there are many molecules or many parts of molecules interacting in this way, the cumulative effect can be quite strong. Van der Waals forces are primarily the mechanism by which geckos use to stick to a glass wall.